Hello, my name is Stefano Berretti and I'm going to present this work entitled the Florence 4D Facial Expression Dataset, which is authored by our group at the University of Florence and our colleagues at the University of Parma, University of Mohamed IV in Rabat, and the University of Lille in France. So, this work is motivated by the fact that facial expression change dynamically, and so they should be studied considering also the temporal evolution of the expressions. And this is true both in 2D and in 3D. But actually there are very few 3D dynamics for the dataset. So in this work we propose a large 4D dataset, which is named Florence 4D, that includes sequences, 3D sequences, dynamic sequences of 3D face model. In particular, in our dataset, we have synthetic and real identities that are combined together, and we are able to generate synthetic expression that changes neutral to apex or expression to expression. These characteristics are something that cannot be found in other existing datasets in the literature. So we have three sources for our 3D models. We have 12 identities from the COMA dataset, which is largely used. We have identities, 62 identities from DA's 3D characters that can be found on the web, and we have 3D scans of real people, 20 real people scanned at our laboratory in the University of Florence. So the first step is that of homologating all these scans in the same topology, in particular that of the DAD Genesis 8 female character. Then using the DAD 3D software, we are able to animate all these static meshes that are in the same topologies and animating them with a large set of different facial expressions. So here you can have an overview of the different identities and how they are split across different ethnicities. So you can see that there is some variability, but the large majority of ethnicities are in the Caucasian one. But we have also some Afro and some Asian ethnicities. Then we have also large variability in terms of expressions. In particular, we consider the 8 main expressions according to the Plutchik wheel of emotions, but we also use this categorization in order to generate more expressions. In particular, you see that for each of these 8 classes we have a different number, which is reported here in the slide, of other expressions that are also summarized here in this table. So there is a main expression, and for each of these main expressions we have a subset of other expressions. For example, for fear we have afraid, ashamed, fear, scream, terrified, worried. All these are in the fear category. And so then we are able to generate facial expressions in 2 different ways. In the first way, we have a single expression animations. So we start from a neutral face, so a 3D scan in this, let me say, coma topology. And then we can generate a synthetic animation starting from the neutral to a peak and then to neutral again. One peculiarity of our generation is that the peak frame is not the predefined frames, but it can change randomly between frame 10 to frame 50, and the overall number of frames is 60. Then we can also generate expression to expression animations. In this case, we start from neutral and terminate the expressions with the neutral one, but in the middle we have 2 different expressions, so we have a transition between a peak expression and another peak expression. And actually this is the first dataset that includes this type of changes that opens the way to different and more elaborating expressions investigations than those that are permitted by existing dataset. Also in this case, we have a randomized position for the peak expression for expression 1 and expression 2. And so this is a summary of the generated expression. So you see that we have a number of single expression sequences, which depends from the number of expressions and the number of identities. And we have also this very large number of combinations of different expressions. So actually at the end we generate all the possible combinations apart those from the same expression. So we have this incredible high number of expression sequences. In order to also validate the difficulty of this data set, we performed a baseline experimentation. The idea is that concentrating on the landmark-based 3D model fitting. So the idea is that of compare the performance on our dataset on those on two other datasets, which are the COMA and the 3D FACS. All these three datasets are in the same topology with the same number of vertices and facets. Actually, from our dataset, we selected a reduced number of, you see here, the 1000 sequences in the 7 standard expressions in order to be comparable with the other two datasets. And we consider, as is always very often done in the literature, we split the identity and the expression. So in one case, basically during the training we have in the expression split, there is during the test expression have not been used during the training. The identity split instead, the identities that are used for testing have not been using during the training. So you can see that actually the reconstruction error is comparable for our datasets to the error that is obtained from the other two datasets, both for the expression and identity split. So this means that the difficulty is, even if the expressions are synthetically generated, the difficulty is the same. So in conclusion, we generated this dynamic dataset, which is made publicly available for public use. And the main characteristic is that we have complex non-standard expression, we have dynamic transition across expression, and we have randomized velocity. And so we hope this can be very useful for the community. Thank you very much.